Hi Chem 101 students. Welcome to the last lecture of this week. So we're going to now be talking about the masses of atoms. So we talked about the mass number for each particular isotope, but in real life, if you pick up a bunch of atoms, you're going to have a whole mixture of all different types of isotopes. So one of your hydrogen atoms, as we saw, would weigh 1 atomic mass unit. Almost all of them do, but some of them weigh 2 atomic mass units, some weigh 3. And so the question is, if we pick up a whole bunch of hydrogen atoms, how do we know what they're going to weigh altogether, since they all weigh different amounts? Well, for that reason, it's really important to have an average atomic mass. Because when we're going to look at a sample of atoms, there's going to be tons of different atoms, and they're all going to be different isotopes from one another, or a lot of them will be different isotopes. And we want to know, for this whole bunch of atoms, how much should the atom weigh on average, so that we can have something that represents all of the atoms together. This is going to be referred to as the average atomic mass, and that's the number on the periodic table I was pointing out at the end of last lecture that we need to want to look at in this lecture. We'll also be looking at a concept called molecular mass. So we'll introduce the word molecule, which is a kind of collection of atoms, and we'll talk about how we can find the mass for an entire molecule and all the atoms within it. So when we look at the periodic table, like with nitrogen here, we see the number up top, and hopefully you remember from the last lecture that the number up top is called the atomic number, and this is the number of protons. So we know that all nitrogen atoms have 7 protons. But what about the bottom here, this number? This number is not the mass number, because remember, when we were talking about mass numbers, those were whole numbers like hydrogen 1, hydrogen 2. This is actually what's known as the average atomic mass. And so this one happens to have a star next to it, because if you look at our periodic table, there's a note about how the average atomic mass actually differs depending on where in the Earth you are. It differs a little bit. And so because there's going to be different amounts of isotopes in different places, perhaps. And so there's kind of a little range to some of them, depending on how many of each isotope there are in a certain place. But overall, they're pretty close together. It's a very small thing. But this atomic weight that's shown on the periodic table is the average weight of all the atoms in the amounts that they're found in nature. So what you're going to see here is, for nitrogen, the average atomic mass is 14.007 atomic mass units, or AMUs. This is because almost all the nitrogen atoms weigh 14 AMUs, but a few of them are nitrogen 15. And so, as we saw in the last lecture, we saw that there are nitrogen 15 atoms that have 8 protons and 7 neutrons, or sorry, 7 protons and 8 neutrons. All nitrogen atoms have 7 protons. And so that drives the average up just a little bit. Although almost all of the nitrogen atoms weigh 14 AMUs, because a few of them weigh 15, on average, the average nitrogen atom weighs a little bit more than 14 AMUs. So, and yeah, just a reminder here, an AMU is about that many grams. It's a very, very small mass. So if we look at lithium, so we look at the lithium on the periodic table, I'll take you there. Lithium right here, it has an average atomic mass of 6.94 AMUs. Okay. Well, if this is because we have a certain amount in the environment of lithium-6, which has a mass number of 6, and lithium-7, which has a mass number of 7. Now, if you look at the average atomic mass, take a guess, which do you think there are more of? The ones that weigh 7 are the ones that weigh 6. It said 7. You're right, because the average is very close to 7. So it must be that most of them weigh 7. And only a few of them have a mass number of 6. So it's true, in nature, there's a mixture of lithium-6 and lithium-7 atoms. And the ratio is about, not exactly, but close to 10% of them are lithium-6. And the other 90% are lithium-7. So let's just do a little thought experiment here about grabbing individual atoms. Now, atoms are so small, there's no way we could grab individual atoms, but let's say that we did. So let's say we grab 10 lithium atoms, okay? 9 out of 10 of these would weigh 7 AMUs, and 1 out of 10, or 10%, would weigh 6. So out of our 10 atoms, if we wanted to average the weight, here's how we average. If you want to take a math average, you add up all of your numbers and then you divide them by how many numbers you have. We have 10 lithium atoms. One of them has a mass of 6. The other 9 have a mass of 7. So we add 6 plus 9 sevens and we get 69. And we divide by the 10 atoms we have and we get 6.9, which is the average weight of these atoms. So close to 6.94. We're not being real exact here. That is the way in which this kind of average should be done. So notice, if you just average the numbers, so this would be the wrong way. If we average the numbers 6 and 7, and we divide it by 2, we'd get 6.5. But that's not the average atomic mass of these atoms, because what we're saying when we do this is we're saying, well, we think 1/2 of the atoms are 6, and 1/2 of the atoms are 7. And that gets you 6.5. Half of 6 plus half of 7 gets you 6.5. But that's not true at all. In reality, it is not half. So it's more like what it really is it's 1 out of 10 atoms are 6, weigh 6. And this, it's not really 1/2. It's really like 9 out of 10 atoms weigh 7. And so if you average this way, you get the same value that we did here. This is what we refer to as a weighted average. Okay, so the average you learned probably in math is like this, where you give 6 and 7 the same weight. And that same weight is 50% or half of the 6 and 50% or half of the 7, because half your numbers are 6 and half your numbers are 7. But that's not true in this situation. 1/10 of our numbers are 6 here, and 9/10 of our numbers are 7. So notice that it looks very similar to a kind of average you'd do in math, except we're not giving each number the weight of half. We're giving it its actual weight of what it actually represents in real life. This is referred to as the abundance. And this is going to be the natural abundance of these atoms. And so that's how we take a weighted average. We don't give equal weights to both numbers. We give them their true weight, consistent with how many of those that there are. So the average weight is closer to 7 because lithium-7 is more abundant. About over 90% of these atoms are lithium-7. So how are we going to calculate the average atomic mass then? Well, this is the kind of problem I'll give you to calculate the average atomic mass. You're going to multiply the mass of each isotope, by its abundance, and then you add them together. Just going back here, that's what we did here, right? We multiplied each number by its abundance, and then we added them. It's just like a normal average, but the weights are not 1/2. They're real weights. Okay, so let's say we want to do this for chlorine. So this is a more realistic problem than our last one. Let me show you a little bit of differences or nuance here to this problem. First of all, chlorine 35, that has a mass number of 35, doesn't actually weigh exactly 35 AMUs. It weighs slightly less, and so we've given the actual mass for chlorine 35. This is because, A weird thing that happens is when protons and neutrons come together and make the nucleus, they lose a little bit of math. This is a nuclear process. I won't say much more about it, but the actual mass of all the neutrons and protons together weigh a little bit less than when they're apart. So that mass in AMUs is 34.968. For chlorine-37, it's 36.965 AMUs. And here we're given percentage of abundance. Oh my goodness, we're using percentage again. So let's recall back to what I told you about percentages. So remember that percent means per 100, right? So 100% means 100 per 100. That's 1. So we can always multiply a number or divide a number by 100% in order to get rid of a percent or get a percent if we want. Here we have a percent and we don't want it. So what I'm going to do is I'm going to take 75.8%, this is percent abundance, and I'm going to divide it by 100%. And what that does for me is that will change my number from a percent to being a decimal. And what we get out of that is those cancel, and we're going to get 0.758. And that is our abundance, 0.758. That is the abundance. So that is the fraction of these atoms, chlorine-35, that are that weigh 34.968. Remember, you want here a fraction, a part of the total that is equal to that amount. So that part is 0.758 written like a decimal. We're going to do the same thing for 24.2%. We're going to make this into a decimal by dividing by 100%. And when you divide by 100%, the percents here cancel. And so then we get our fraction, or our decimal, really, number less than 1. So that is 0.242. And so now we have turned our percent abundances into abundances. And now what we're going to do is the mass of each isotope times its abundance. So we're going to do the mass of chlorine-35 times the abundance of chlorine-35. And we're going to add that to the mass of chlorine-37 times the abundance I'll just call it abundance of chlorine-37. And that's all the isotopes. You would keep doing that until you have all of them. But in this case, that's all of them. Okay. And so that's how we're going to figure this out. All right. And so if I write this in now, my head's in the way, but mass times abundance plus mass times abundance. Okay. So now we want to calculate the average atomic mass. That's how you do it. So let's write down the numbers here. It's going to be 34.968 AMUs times 0.758. That's the abundance, not the percent abundance, but the fraction that is those. Then we're going to do 36.965 AMUs times its abundance, which is 0.242. Okay. And so that's what I'm going to have on the next slide. And what I'd like to do now is break this down for you in terms of significant figures as well. Okay. So we have the average atomic mass is the abundance times the atomic mass plus the abundance times the atomic mass, and we keep on going. So this is what we had on the last slide. The abundance here times the mass plus the abundance times the mass. Now when we multiply these, remember when we multiply, we count sig figs here. So this guy has 3 sig figs. This one has 5 sig figs. So what we're going to do is we're going to make sure that our result here has 3 sig figs. Down here we also had 3 sig figs for this one and 5 sig figs for this one. Okay, so let's multiply these. Oops, got the wrong one up there. Okay, there we go. I'm going to multiply these now. 0.758 times 34.968. Okay, and so we get 26.5 blah 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 blah, and it goes on and on. We should remember that we've only got 3 sig figs, so our last sig fig is the 5. So when I write this down, I'm going to write this down as 26.505. I can write more, but I need to remember that the 5 is my last sig fig, so I can underline it like that way. You could round it too if you want. Now let's do the same thing here with the 0.242 times 36.965. And we get 8.94. Now for this one, 8.94. Here again, we're multiplying, so we count the sig figs. And there should be 3 sig figs, so the last sig fig here is the 4. And we have 553 past that. 553, but those are not significant. The last sig fig is the 4. So you'll see here when I wrote these down, I made sure that I underlined my last sig fig so I could remind myself of the place value of the sig fig, because now what we're going to be doing is adding. And when you add and subtract, you look at the place value here. And so the place value of this one is at the tenths for the last sig fig. Place value of this one is at the hundredths. So when we add these, you should be adding them like you're in grade school, right? I should have lined these up a little better. I'll rewrite this one. So you want to line them up like you're in grade school. So you're going to put, we don't need all the extra digits, but I can keep a couple. So it's going to be 26.5, and that's the last sig fig, 0.5. Now these ones I wrote them, but they're not significant because we were keeping track which ones were significant, which ones weren't. And so when we add these, we get 26.505 plus 8.9455. We get 35.4505. 35.4505. But because the 5 here is at the tenths place, we have to round at the tenths place. And these are AMUs, by the way. AMUs. AMUs. So our result will be what we have at the bottom, 35.5 AMUs. Okay, and that's how you determine the average atomic mass for a substance, or for an element. Notice again, we're going to have abundance, and these abundances are less than 1. You could be either given the abundance directly or the percent abundance, like we were in this problem. If you get the percent abundance, make sure to divide by 100% as we did and turn this into a fraction, a less than 1 number, decimal here, to get the abundance there. And then you multiply those each by the mass and you get the average atomic mass. And that is what you see on the periodic table. If we look at it for chlorine, let's go look at our periodic table for chlorine. We see that it is 35.45, the average atomic mass there. And here's that star on the periodic table I mentioned earlier, there are a couple of different weights for, there's basically a range of the potential weights, but that's just being very picky about these. This is new information from the authorities on chemistry in the world. Okay. So now I have one more thing to talk with you about, and my molecule popped up. I didn't think that was going to pop up, but it's behind me here. Anyway, here's a picture of a molecule. So what is a molecule? So molecules are groups of atoms that are stuck together in a particular arrangement. So if you see the one by my head, they're stuck together in this arrangement where there are these white spheres, which represent hydrogen atoms, stuck to a black sphere, which represents a carbon atom, and they're distributed around the molecule, around the carbon atom, in a certain arrangement. The atoms that are stuck together in this way are said to be in a chemical bond, and we'll talk about why chemical bonds happen very soon. They essentially happen because electrons, which are negative, are attracted to protons, which are positive, and the neighboring atoms have protons, so the electrons can be attracted to them, and that can help to stick the atoms together. A water molecule, for example, has two hydrogen atoms that are bonded to one oxygen atom, and we describe that with the formula H2O. The subscript here 2 indicates two hydrogen atoms and one oxygen atom, and the molecule looks like this. Two hydrogen atoms attached to one oxygen atom, which is represented by the red sphere here. Or another example molecule, methane, which is the natural gas you use to cook on your stove, or probably heat your water or heat your house. This has a chemical formula CH4. It has one carbon atom, the black one, which is attached to four hydrogen atoms, which are these white ones here. So what we want to do is use the purpose of these average atomic masses is actually to determine the masses of, often it's to determine the masses of molecules. So to get the masses of molecules, we need to add the average atomic masses of all the atoms that make them. Now it's important to note that this is not going to be the mass of any particular molecule, right? Because we know that atoms can have different numbers of neutrons and weigh different. Not every hydrogen atom weighs the same, or not every oxygen atom weighs the same, or carbon atom. But this will give you the average mass of a particular molecule, which will be useful because if we're going to do chemistry later on with a whole cup of water, that's going to have tons of water molecules in it. What we want to do is find ways of knowing how many water molecules is that. But the only way we're going to be able to know that is by weighing it. And so we want to know what will be the average weight of these molecules, so that when we have a bunch of them, we're looking at, you know, the average weight of what these molecules might be. And so let's see how we can determine the average atomic mass for a molecule. We were going to call this the molecular mass. So that's what's going to be the name of that. So to determine the molecular mass, you'll add up the masses from each atom in AMU, so from the periodic table, and multiply that by the number of those atoms that exist. By the number of that atom. So for example, if we want to get the molecular mass of water, H2O, okay, well, we're going to do 2 times the mass of the hydrogen atom and add that to 1 times the average atomic mass of the oxygen atom. And so we go in the periodic table, and this is what we're going to be using the periodic table for. It's going to have even a better use as we move on that will work very much in the same way we're using it now. But we'll look, okay, and we see the average hydrogen atom weighs 1.008 AMUs, and the average oxygen atom weighs 15.999 AMUs. Okay, so that's what we're going to put in here. For hydrogen, we're going to do 2 times its mass, 1.008 AMUs, plus 1 times the average atomic mass for oxygen, 15.99 AMUs. And so we get 15.0 18 rather, 0.015. We can add those together. The calculator here. 2 times 1.008 plus 1 times 15.99. Oh, I forgot my 9, that's why. There should be a 9 here. Let me add that. And we'll see, we'll have ways of deciding how many of these numbers from the periodic table we want to write. We don't always have to write them all, even though I am doing it this time. So 2 times 1.008 plus 1 times 15.999 equals 18.015 AMUs. Let's do this one more time for methane. So methane from the last slide was CH4. So we're going to do, for the molecular mass, we're going to do 1 times the average atomic mass for carbon plus 4 times the average atomic mass for hydrogen. Now, if you're watching the video, I want to encourage you to try this by yourself before I show you. So you can pause it here, give it a shot. And now I'm going to show you the answer. Pause it if you don't want to see it. Okay, now I'm going to show you the answer. So it's going to be 1 times the mass for carbon. So we look that up on our periodic table. That's going to be 12.011. So we do 12.011, and these are AMUs. That's going to be plus 4 times the one for hydrogen, which we still have right here from the periodic table, is 1.008 AMUs. I'm trying to dodge my head here. Okay, and so we'll put that into our calculator. So it'll be 1 times 12.011 plus 4 times 1.008 equals 16.043 AMUs. Now, as I said, we used all of the digits from the periodic table this time. Later on, we're going to be doing something very similar, except it will be in units of grams. And at that point, I'll teach you how to decide how many of these digits that you'll want to choose. Because if you look for some of these, there's a whole lot of digits, especially if you look at other periodic tables. They list so many digits for some of these. But we'll only need to take however many digits as we need, depending on how we will apply this later. Okay, and so that's the end of the material for this week, for week 3. And so I encourage you to study this material hard, and also for this week, I know last week was, a kind of tougher week. I spent more time on the videos because it's just, even though the number of pages in the book isn't as much, I feel like it's useful to talk a little bit more about it. So I'll be continuing to emphasize sig figs as we do these calculations. You'll notice I continued to talk about sig figs the entire time we were doing this. Sig figs will continue to be important. Also, so will conversion factors. You'll notice we applied conversion factors as well in some of the earlier lectures this week. And so please do not hesitate to ask me questions, even if it's about previous weeks. I do want to make sure that you feel solid about last week's material. Anyway, good luck for this week, and I'll see you in office hours. One more thing is, as I sign off here, you are going to see in this week's material a survey. So for next week, I'd like to expand or move my office hours to make sure that I'm giving you guys as much time as possible. I do have other commitments, like I have a Chem 151 lab I have to go in on Tuesday and Thursday morning. You'll see that I don't offer that as one of the choices, and I do have office hours with them as well at other times. However, I did try to offer a range of choices, and I also will ask you, or I've asked you on the survey when you see it, what other times might be useful to you. Now, I don't usually study late or teach late at night. So most of my times I offered were during the day, but a little later in the afternoon isn't so bad. If you know if it's just missing your work hour or something, or but I do encourage you to come to the office hours that are there as well. I know I won't be able to. It's never possible to put office hours that are convenient for every single student, so you can always, talk to me about that personally. Please do not hesitate to reach out to me. There's some of you I don't know yet, I haven't heard from. I'd like to hear from you. I'd like to get to know you better. I'd like to know what questions you have. Especially when I was grading the homework, I noticed some people really should have talked to me. Please don't be afraid to talk to me if you need some help. I know we're separated by a distance, but I do want to help. So anyway, that's it for this week, and I will see you guys later this week in office hours, hopefully, or on the next video.